Here in this video, we are solving two questions from semiconductor devices. Both are simple theoretical questions, conceptual questions. Let us see what is that question is. The first question says, the electron concentration in n-type semiconductor is same as the hole concentration of the p-type semiconducting material. So the first thing you need to know that there are two types of semiconducting materials called at a broader level, intrinsic and extrinsic. Intrinsic is something like a pure semiconducting material where number of electrons equal to number of holes. Extrinsic is done by doping, by adding a element with a smaller magnitude so that it will have either electrons dominating or holes dominating. If electrons are dominating, then that's called n-type material, where electrons are majority carriers. P-type are someone where holes are majority carriers, electrons are minority carriers. It is given that number of electrons in a n-type material is number of holes in a p-type material. An external field, further it is said, is applied across each of them. Compare the currents in them. So whenever an external field is applied, both semiconducting materials, that is silicon and p-type and n-type, will pass the current through them, and we can derive an expression for the current in that semiconductor material as N E A V D. Let us know each of these terms, what are they are. N is the number of electrons per unit volume, number of charges or free charges or majority carriers per unit volume. E is the charge of that, here electrons and holes have the same charge. A is the area of cross section, and Vd is called something like drift velocity. That is the constant velocity acquired by a charged particle when it is passing through a semiconducting material after it is suffering multiple collisions. It can be further said that, it can be further proved that drift velocity is mu into E, where mu is called mobility of that free charge, and E is the applied electric field. E is the applied electric field. So if I have to write the current in either p-type material or n-type material, I can write it as I equal to, as per this equation, NEA in the place of VD, I can write mu into E, where mu is mobility. So if you compare for n-type and p-type material, number of electrons or holes per unit volume are same, charge of hole or electron is same, area of cross section is same, for the conductor is same, applied electric field is also same. So the only difference that is available here is how much current passes through a given material is simply directly proportional to mu, which is mobility. But it's a known fact that mu of electrons, mobility of electrons, is much greater than mu of holes, approximately 2.5 times of the mobility of the holes is the mobility of the electrons. Holes have electrons have a mobility 2.5 times that of the holes. That implies as mobility of electrons is greater than mobility of holes, current due to the n-type material is greater than the current due to the p-type material. So answer C, current due to the n-type material is greater than the current due to the p-type material is the right answer for that problem, right? Let us see what is the next question is. That appeared in NEET 2021. Consider the following statements A and B. First question. A GNR diode is connected in reverse bias when used as a voltage regulator. So I think you can explain entire voltage regulator phenomena, but I will quickly explain what happens is, first of all, a GNR diode is a PN junction diode, but a little more doped, highly doped PN junction diode. So what happens in the case of a highly, because it is a highly doped PN junction diode, the first thing is the breakdown voltage of GNR diode is not that high like a PN junction diode. Means what? It can pass current even in the reverse bias, provided if you apply a input voltage that is more than the breakdown voltage. Breakdown voltage means it's the reverse voltage applied at which the diode start passing current. So you shall connect this PN junction diode, that this GNR diode, in reverse bias, so that it can work even in the reverse bias. That's why in fact we use a GNR diode. If you need a diode that passes the current in forward bias, you are very much having that regular PN junction diode. The problem with the PN junction diode is it has a high breakdown voltage, so that you cannot use it in reverse bias. But this GNR diode has a low breakdown voltage, so it can be used in reverse bias. That means for this positive we will connect a negative like this. So I have connected it in reverse. So what happens is, when the input voltage, whatever you have applied, is the GNR diode voltage, VGNR diode voltage, it start passing current through it. That means some output is available. So here you give some voltage. Of course, here you connect a resistance called something like series resistance. You can read the entire working of a GNR diode in the playlist of semiconductor devices I have made. I am not going into the details. But what we can say is, when the input voltage is, if Vi is greater than VGNR diode, what happens is GNR diode will take only VGNR even if it is more than that, and the output, whatever may be the resistance that you are having, load resistance, being parallel to GNR diode, voltage across GNR diode, across the load resistance, is equal to the voltage across GNR diode. Thus, voltage across the load is voltage across the GNR diode. Voltage here is whatever may be the input minus VGNR diode. To take care of that only this series resistance is there. So in a nutshell, what is given here is right. Statement A is right. Let us see what is statement B. The potential barrier. Potential barrier means the voltage at the junction. So if we have to see how does it works in a PN junction material. This is a P-type material, this is a N-type material. Here the diffusion happens, and because of the technical reasons how it works, please see through the video I have made on this potential barrier. Opposes the flow of the current, that is called V barrier, barrier potential. So that barrier potential is anyway definitely there for a semiconducting material. It depends on the nature of the material that we use to make this semiconducting material. The known fact is barrier potential for germanium is approximately 0.3 or 0.35 volts, and for silicon, the other material through which we make semiconducting materials, barrier potential is approximately 0.6 to 0.7 volts. But it was given that barrier potential lies between 0.1 and 0.3. It cannot remain at a maximum 0.3. It can go to a maximum of 0.7. Thus statement A is correct, and statement B is wrong. Actually, sorry that here there is only two options available. There shall be availability of a third option, option C, where A is correct and B is wrong. That's the right answer. That's the right answer for the problem. That's how you have to understand the basics so that you can solve the problems, simple problems, conceptual problems. Thank you for watching.